The next application is Venturimeter. Venturimeter is it is a device used to measure the velocity of velocity of water flowing through a pipe. Okay, velocity of water or some liquid flowing through a pipe. So let's take that pipe. Second application. Second application is Venturimeter. Venturimeter. So suppose this is the pipe where water is flowing through. Okay, water is flowing through this pipe. Now we have to find the velocity of this water flow. What we do is we break this and we connect a smaller pipe like this, smaller radius pipe like this. So at some point we have to again connect to the existed one. Then we need some vertical pipes connected to these two pipes like this. These are open like this. Okay, now a liquid is flowing. Let's take this streamline. So this is one of the main places, and this is another main place. That means high area place and the low area place. Okay, let's take velocity at this tube as V, and pressure at this place as P1, and area as A1. Area as, let's take as capital A. Let's name the place as X place, and let this be Y place. Let's take the pressure of this place as P2, velocity at this place as U. If cross-sectional area at this place is capital A, let's take cross-sectional area at this tube as simple A. Now we know simple A is smaller in area, so velocity should be high. If the velocity is high, pressure is low. At this place the pressure is small. So when we consider this tube, velocity is small, so pressure is high. Therefore liquid in this tube will rise up in this tube for a height like this, but in this tube it won't rise for the same height. Let me explain that again. Here when we consider velocities, here velocity is small, here velocity is large. If the velocity is y, here area is large, here area is small. So therefore in near smaller areas velocity is high. If velocity is high, pressure is small. So liquid will rise up to a smaller height. Here, due to high pressure, low velocity and high pressure, this pressure will push the liquid more than this tube. Okay, so let's take the liquid's height as this as h1, and height here as h2. This as h2. Okay, now what I need to find is the velocity of water flowing through this pipe. Through this pipe means I have to find the velocity of water flowing in the initial pipe. That means not this pipe, not the smaller one, but the initial one, this larger one. So let's find an expression for this u first from the equation of continuity. That means using a1 v1 equal a2 v2, let's apply to these two places. Capital A times capital A v, velocity is v, equals simple A u. I need u expression for u equal simple A over capital A times V. Okay, now let's apply Bernoulli's equation for these two places. I have to write like that, considering x and y points along the streamline. Along the streamline. Let's apply the Bernoulli's equation. P1 plus kinetic energy by unit volume is half rho V1 squared plus, when we consider the potential energy term, there is no potential energy. Why? Because these are horizontal tubes. So therefore, it get cancelled out. So these are horizontal tubes. So we just have the other side, P2 plus half rho V2 squared. Not V2 squared. It is actually U squared. We can't take V1 here because we already took. Let's just straight away take this V. This is V squared equal, this is P2, it is okay, P2 plus half U square. Velocity is U here. Okay. Pressure 1, P1. Pressure at these places, it can be written as, this is open to the atmosphere, right? This is open to the atmosphere. That means at this position, it is at atmospheric pressure. So atmospheric pressure plus H rho G equal to pressure at this place. Atmospheric pressure plus H rho G equal to pressure at this place. So P1 is actually pi, atmospheric pressure plus pi is a term used to denote atmospheric pressure. So PATM is equal to pi. Sometimes students take as P naught, but this is not that good to use P naught. Either you can take PATM or pi. Pi is easy to write. So pi plus H1 rho G is the pressure at this point. Why? Pressure inside the liquid is given by H rho G term. Pressure inside the liquid is given by H rho G term. For that you have to include the atmospheric pressure also. Plus half rho V squared equal P2. In the same way, I can write P2 as pi plus atmospheric pressure plus H2 rho G, H2 rho G plus half rho U squared. First, we can cancel pi from this place. After cancelling pi, we can cancel rho because rho is in all those terms. We can cancel rho only after cancelling pi first. Why? Because rho is not in this pi terms. Therefore, first we have to cancel pi. That means we are subtracting pi from both sides. Then we can just remove pi and we can cancel the rho term. Then we get, after that we get, let me multiply everything by 2. So here I will get, I'm getting 2 H1 rho plus V squared equal 2 H2 rho plus rho. No, rho we cancelled, right? We cancelled out rho. It should be not rho, G. 2 H1 G V squared. 2 is not there anymore. Why? Because we multiplied by 2. Here we get 2 H2 G, and here I have only U squared. For U squared, I can substitute this one. So it is A squared over capital A squared or simple A squared into V squared. Right. I have to subject v. Actually, I have to subject v here to find the velocity v. I have to subject v. What is the large height? H1 is the large height, so I will take this to this side. So I can take 2g common and write h1 minus h2 equal, I can take this to other side, and also I can take v common, v squared common. So this is 1, right? Plus v squared becomes minus v squared, and I'm taking v squared out. So finally equal v equal to what? I can take this whole term to denominator, 2g h1 minus h2 divided by a squared over simple a squared minus 1 and square root. This is the final expression for the velocity. As soon as you see this expression, you have to get that idea. We are not going to use this by remembering or recalling like that. We'll just have to derive the equation if we come to a place like this. It is not that difficult. If we get a sum or something like that, most of the things will be simplified from the first line itself. So we won't be getting some complicated simplification like this. If we are getting values, we can simplify just from this line. Okay, you have to write all these things in the space given. Start from the diagram and write this and this section.